So nobody conducted a study in which they just simply observed somebody stuffing their face with 99 brownie bites and then just kind of let nature take its course, or run its course. It's not a good thing to do. So let me clear out my data from yesterday. It says second plus, clear all lists. Says done. Now I got a fresh editor to work with. All right, start typing in values. All right, so that's the first list. I really got to set like an alarm for myself during period 6 because I get engrossed in whatever I'm working on, and every day I want some kind of reminder for myself to actually type the data in, at least for the first problem that we're working on, so that we don't have these moments where you're like, oh, okay, this is fun. This is how you type data in. It's so exciting. All right. That's the thing. Data entry jobs. They're not fun. Right? Like you're not typing stuff into a TI calculator. It's actually so much worse than that. Like the first time you go to a doctor's office and they have you fill out all those forms, somebody's got to type all that into the system. That's the data entry position. Oof. I mean, I look at this as like, oh, this is so boring. Like just typing in like 12 values or whatever it is, 10 values, 10 pairs of data. You got to type in somebody's name based off their handwriting. Oh, brutal. All right. So visually determine the best fit model. All right. I don't know why I put blanks here. I never do that for any other problems. I'll take that as those as typos. All right. So. And also, it's like visual. It's a directive. It's visually determine the best fit model. I never said to actually write anything down. So we'll say rephrase 1A and get rid of the line in 1C. Right, so for those of you who need typo bonus, that's my gift to you. All right, so just making sure that the plot's set up and ready to go. I check my y equals to make sure I don't have any nonsense in there. Zoom 9. That definitely does not look linear. Thank you. It definitely doesn't look linear. You can make a case for really a bunch of different possibilities here. Well, ignore the standard linear. Is it exponential? Is it polynomial? Now, polynomial is a rough one because you could have any power associated with a polynomial. Like what degree of a polynomial will we be looking at? Is it quadratic, cubic, quartic, quintic, and so on. I mean, you could have a high power of like 32 if you want. Right? But the thing about polynomial models that's tricky is, I mean, if you think about a polynomial, like just an ordinary x squared function, it's got one turning point, right? A cubic function can have 2 turning points, right? Often it doesn't. Sometimes it just increases, levels off, and increases again. But then there's other instances where it increases to a maximum, decreases to a minimum, and then increases again without bound. All right, so 2 turning points. For a quartic, that's the W-shaped graph or the M-shaped graph. Right? So that's 3 turning points. So you always have the potential for at most n minus 1 turning points. Whatever the highest power is of your polynomial, 1 less than that is the maximum number of turning points that you can have. What that means is that if I go sufficiently large with the power of a polynomial function, I can get it to go through every single one of the points. It's just a matter of coefficients. It's also a question of whether that's meaningful, right? So you look at a polynomial model and say, okay, well, if I do a 10th degree polynomial, that's going to be a great fit. But what does it mean? We don't know. Right? Contextually, it's probably not a good idea. Right? I'm looking at the context here. Brownie bites eaten, individual male's weight. Right? So the first thing I'm going to ask myself is, can either of these variables increase without restriction? All right, without bound. So can you have an infinite number of brownie bites on a daily basis? And will the weight ever approach an infinite destination, if you will? All right, the answer is no on both counts. Now get into negatives. Can you ever have a negative number of brownie bites? That would be disgusting. All right, so no. Negative weight, also disgusting. So no. All right. So we would want to restrict whatever model we come up with so that it doesn't go into the negative space and it doesn't increase or decrease without restriction, right? Without bound. So what does that mean? It means I want some asymptotes in here. I want a function that has an asymptote, right? Or something that levels off, right? Like a log function, it doesn't have an asymptote, at least a horizontal asymptote, it has vertical, but it does have that leveling off capacity, right? A reciprocal model, like a rational function, those have asymptotes, right? So I'd be asking myself, is there some maximum weight that this individual could ever achieve, at which point it doesn't matter how many brownie bites they eat, they're just never going to get any heavier than that? I mean, I would think probably yeah. Because if you eat enough brownie bites, the volume of your body could possibly be overtaken by the actual brownie bites. All right, all the empty space within your body. Like, you have a maximum capacity. I mean, at some point you're not going to expand anymore without, like, I'm just thinking of the Willy Wonka. Yeah, like, what was it? The character was Violet, I think. The one that turned into a big giant grape or whatever it was. So, like, you're thinking about something like that. Eventually, you get to a maximum size, and that's going to be the end of it. All right. So, yeah, in the most gruesome, horrible way possible. So I'm thinking logarithmic or reciprocal. All right. A power model, you think about a power function. So y equals x squared. Y equals 4x to the third power. All right. A power model can also involve reciprocal functions, but you're really just looking at any instance in which you have coefficient variable exponent. So think of a polynomial function, but only the first term. All right. So the first term, ignore everything after that. All right. So for the same reason I wouldn't want a polynomial, I wouldn't want a power function either. All right. Exponential, same idea. With the polynomial, contextually, what are we looking at? Is it something that would increase without bound? No. All right. So we're living in the world of reciprocal or polynomial. All right. So visually determine the best fit model. Well, I'm just going to say it's reciprocal or I think I might have said polynomial. Logarithmic after all that. All right, this gives us a place to start our investigation. All right, determine using your calculator the best regression model. Why is the one you chose the best? That's going to come down to the r squared value. If the r squared is closer to 1 for a reciprocal or a logarithmic function, then we would make that decision. All right. So what that means is we have to perform the transformations. Now you could use the table here, but the idea is for you to develop understanding or intuition related to what type of functions you're looking at. Right? When you're dealing with a reciprocal model, it's actually pretty straightforward in the sense that you take an ordinary function, linear function, and find the reciprocal of it. It would be 1 over whatever that function is. Right? So if I say, I was going to write it on the board, but I'll do it on the screen here. For a reciprocal, or a rational function, we'd be looking at something like y equals 1 over a plus bx. All right. So you take your ordinary linear function and flip it. That's what a reciprocal would do. All right. So if I want the actual regressed model, I just throw on the trimmings here, a little y hat, and call it a day. Bless you. All right. The other possibility is the logarithmic. All right. So it would be in this form ultimately. But basically, if you think about the linear equation, a plus bx, we're saying a plus b times the log of x. All right. So it's really just replacing the independent variable with the log of x. You could actually kind of go a different direction with that, but it gets unwieldy in terms of the numbers. Like if you decided to raise 10, for example, to the y power, you know, because you perform on y the opposite of whatever it is that you're trying to do for x. All right. So if I'm looking for a logarithmic model, I would apply for x, I would apply an exponential model to y, right? Because it's an inverse relationship. But using a base 10 as an exponential is just it's a nightmare. All right. So we start with the reciprocal, and then we get onto the logarithmic. And again, it's up to you if you want to go with a natural or a common log. The AP folks tend to go common log, but you could really go either way. The reason they go common log is because when you create a log scale, it's easier to go in terms of tenths, you know, hundredths, thousands, and so on than multiples, or I'm sorry, powers of e. You know, so a plus b log x is really what we're after here. All right. So you see in the table they use BO and B1. I forget where I got this from, probably a textbook somewhere. A and B instead of the BO and B1. Yeah, question.
When we're doing logs, will we always just assume a base of 10, or will we have cases where the variable is the base?
We're not going to have cases where the variable is the base, so we're always going to assume base 10. All right, so into the table, stat, edit. Start off with the reciprocal. Now, I can, in order to create this function, I can do a couple of things. I suppose one would be to actually take the reciprocal of the regressed model, but that's a little trickier. So what we do is, you know, just follow this dependent variable relationship, but I'll show you where it comes from in a sec, where we say the dependent variable, instead of being y, we say it's 1 over y. And the reason we can do that is it's just ordinary algebra, right? I cross multiply, I get y hat times a plus bx is equal to 1. You could also just switch them. If I solve for a plus bx, I get 1 over y. In this case, y hat. All right. So what I would do is find the reciprocal of y, because that's just going to be an easier computation. So 1 over, so in L3, 1 over L2. I didn't even bother with the ordinary linear regression, because we looked at the picture and a linear regression is just not appropriate. So I just jumped right to this, but you could also check for the linear case.
So could you do 1 over y1 if you store the regular normal ones instead of having it?
Yeah, so that's what we'll get to. Yeah. So L1, L3 is what we're going to regress. So stat, calc 8, L1, L3, I have it from yesterday, so that's good. Alpha trace y1. Starts to become muscle memory after a while. You do it so many times. Enter. You have this model here. Now, it's tempting to write all this stuff down and call it a day, but we don't know if this is the best fit model. Right? It looks pretty good, though. 0.854, roughly. we can have a look at the graph. All right, so the r squared value is approximately 0.854. All right, so I want to be able to compare that to the log case, which we'll get to in a sec. All right, so you go into your y1. This is a linear regression between the transformed variable y, which became 1 over y. So if I graph this line, it's not going to be anywhere near the curve, or I'm sorry, the scatter plot. So we don't want to do that. What we do, turn that one off, and plot 1 over y1. All right, because our model should be in the form of y hat is equal to 1 over a plus bx. So this is my a plus bx for the transformed data. 1 over that is going to give me the appropriate model. Which, even though we got a pretty good r squared, doesn't look anything like the scatter plot. All right, so I'm not inclined to go with this one. I wanted something with an asymptote. The problem is the relevant asymptote is nowhere to be found. All right, so I was hoping for something that would bow the other way. You know, so it's more likely that it's going to be a log. All right, but according to our computations, 0.854, that's not a bad r squared value. This is a pretty good fit for the data, but I'm just looking at it and saying, oh, I mean, it may numerically be a good fit, but it's definitely not a good fit visually, and it's definitely not a good fit contextually, right? Because it's going to increase without bound. Right, so we'll have a vertical asymptote in the worst possible place. All right, so scratch that. Good thing we didn't write down that whole equation. Stat, edit, go to the log. Again, logarithmic model. The independent variable is log of x. All right, so yeah, because if you want your equation to be in this form, a plus b log x, I mean, we could solve it for x, a plus b x, like we did for the other one, but that's going to be a nightmare algebraically. All right, so what we do is we leave the y alone here and find the log of the x values. All right, so log of L1, and we regress L3 against L2. All right, because L3 is the independent variable, L2 is the output. It's the response variable. It's the dependent variable. So I'm going to do my linear regression, stat calc 8, L3 against L2. And I'm going to store the regression equation, alpha trace y1. Run the calculation. That's a really good looking r squared value. All right, so my r squared here, approximately 0.939. All right, so then I go to y equals 1 over y1 doesn't make sense anymore. If my final equation is going to be in the form of a plus bx, a plus b log x, and what we have is a plus bx, then what we can do is go right on in there and just make the adjustment. All right, right in front of the x, just tuck in a log. Then graph it. Now that's a pretty good fit right there. All right, so it looks contextually and visually like what you would expect it to look like. Something that increases and then levels off at a slower rate. So what's the equation of the best fit model? Right, it's this whole thing. All right, you can round it, of course. So negative 109. So y hat is going to be negative 109.899. Then go on down the line. 208.963. That was positive, I think. Times the log of x. All right, so Now we evaluate, you do a little extrapolation. I'm trying to determine whether this makes sense using a couple of examples. What weight would you expect a person who eats 100 brownie bites per day to be? That's saying what's y when x is equal to 100. So y hat of 100. All right, so alpha trace y1. Pop in the 100. And you get 308.0274. All right, so according to our model, are pretty close to 310 pounds, but our data set has 99 brownie bites corresponding to a weight of 325 pounds. All right, so clearly there's a discrepancy, unless this is a situation where you have like the magic brownie bite diet that, you know, like you just got to tough it out and eat 100 brownie bites and then you'll start losing weight. You know, I doubt that's the case. So, you know, we're going to assume some amount of error here. All right. And it kind of makes sense because, you know, we discussed the concept of a residual. A residual wouldn't exist unless there was some error between the observed and the expected values. All right. How many brownie bites per day would you expect a person who's 150 pounds to eat? So we're saying y hat of some value x is equal to 150. All right. You could use a solver in the TI if you want, but you could also just use the graph. So just type in 150, y equals 150, and find the intersection. All right. If it didn't show up on the graph, I would expand the window, but it does, so we're in good shape here. So second trace 5, right, intersect. And since there's only one intersection on the screen, you could just hit enter 3 times. And you get about 17.529. So x is about 17.529 brownie bites. All right. Now, if you want to use the solver, you know, it's not the most user-friendly application in the calculator, but it does the work for you without having to come up with a graph, which is good, you know, because sometimes the window is just a pain. All right, so math, go on down to the one that says solver. It might say numeric solver if you have one of the fancier calculators. All right. If it has this display, then you just put in your equation just solved for 0. Right? But the newer ones actually have a better window where it says equation 1, equation 2, and you just put them in. So in this case, I'm looking at the y equation, y1 needs to be equal to 150. That's ultimately what I want, which means y1 minus 150 is equal to 0. So that's what I would type in here, alpha trace y1 minus 150. Hit enter, and then, I mean, it already had the answer stored in from the graph approach, but you just put in any value that you think is reasonably close to whatever the solution is. Right? So basically something in the domain. Right? We're looking at only having one solution, so it really doesn't matter what I put in. So let's say I put in 5, and then hit alpha enter. You see it says solve there above enter. Hit alpha enter. And within the domain, that bound, that's the statement of domain. Within that domain, it'll come up with the equivalence relation. So whatever value allows for y1 minus 150 to be equal to 0. All right, so hit alpha enter, and it gives you the solution. All right, and that works with any function-based equation. So it's a pretty good feature. I think I can change the type of calculator here. Let me see real quick. So math, go on down to numeric solver, and it'll look like this. All right, I'm pretty sure I just lost my equation here, so that would be an issue. But you would type in, for the first equation, whatever the left side is, y1, alpha trace y1. For the second one, type in the 150, go down to OK, and then you just do the alpha enter thing here. Right, but since I don't have anything in y1, it's not giving me a field to put that in, so I'll just do just make up an equation. Let's say 2x plus 20. All right, so then they call it a guess, but it's not really a guess. It's just you having a sense of the domain and where the solution would exist, and so more like an educated guess anyway. But let's say I think that the solution is 6, hit alpha enter, and it'll solve it for you. All right. But then sometimes it gives you these, like the 0.99999. Calculator's trying to say 65, but it's having a hard time with it. All right. But again, this is just a made up equation. But then you could check it out and you say, if I put a 65 in here, I get 130 plus 20 is going to give me 150. All right. So it's kind of a nice feature on the calculator, but it's maybe a little too convoluted. Right? As far as Desmos is concerned, come on, get out of here. As long as you know what kind of function you're looking to investigate, you can use the regression feature on Desmos to at least check your work. You just can't do it to actually do the work, because we need to use the transformation technique. Not just, like if I want a cubic regression, I don't use cubic reg in the stat calc menu. So it's the same idea here. All right, but you could use tables in Desmos to get that, can't think words, data set populated. So, I just pop in the 12 with my fat fingers. So here we go. Really wish I typed this in before, also didn't, so here we are. Yeah, so I'll try to multitask here, but yeah, you see I already failed at that. If you know the structure of the function that you're trying to generate, then it's really just a matter of typing that in. So in this case, I wanted y is equal to a plus b log x. So that's actually what I'm going to type in mostly. All right, so, okay. The thing is, we're referring to x1 and y1 here, not x and y, because data is stored in the table and the column headings are x1, y1. All right, so the way we would write this, if I wanted to do a linear regression, it would just be y1 tilde a plus bx. But if I'm doing any other type of regression, I just use whatever the predicted value form would be. All right, so in this case, I would write y1. I got to find the tilde. There it is. Then a plus b, not x, but log x. So log log. And it's a base 10 logarithm, but it's log of x1. All right. So it'll give you the answer, the transformed equation, which is great. I mean, if only you could do this on the AP exam. But yeah, you'll get the answer. It'll be great, but it's not enough in terms of the amount of work that you'll have to show. All right. So anyway, so that's pretty good. Now, in terms of the actual graph, with Desmos, there's no zoom 9, so you just got to kind of get into the neighborhood of the points, and then you could look at the graph from there. Right. Yeah, so it really is just a matter of typing in the predicted value model. right? So if I wanted to do a reciprocal model, I would actually just type in this. You could use a subscript notation if you want to. I mean, if you want to make it like true to what you see here on paper, then you could actually type in what you see. That you're not going to get the hat to show up, but you don't need that anyway. But you could do a b sub 0 and a b sub 1. But if you type in 1 over a plus b times x, then it'll show up just the way we did it the long way. The one thing that you got to be careful, one of the many things you got to be careful about when you use Desmos, is once A and B have been used, you can't use them again. All right, so you use them for this regression, and then you try, like in the next line, to do it again using A and B. What's going to end up happening is it's going to take the A and B value from this computation and use that in your new regression attempt. All right, so it'll foul the whole thing up. So you don't want that. All right, so very important. One of two possibilities here: change up your variables. You used A and B here, use C and D next time, or create a different Desmos. All right, so just copy the data over into a different Desmos and go from there. All right, so I know it's a pain, but it is what it is. So in terms of data entry, I think at some point we talked about importing an image into Excel, but the way you have to store the data, let me just pull up something here. I got something, whatever, I'll take this one. If you have data already in Excel and you want to go to Desmos, so let me open a new window. All you have to do is go into a field and paste it right in, and you'll have all that information, right? So that's a real good benefit of having data already stored in Excel. So let's say you have it, like we're taking a test on Schoology or something like that. I hit the wrong thing. And you have the ability to copy and paste your data set. You just pop it right into an Excel spreadsheet. So I'll just open one here. So insert. We're going to do data from picture, picture from file. It was my most recent screenshot. You do that. It runs through to make sure that it's getting the data correct. All right, so insert the data. Insert it anyway, don't really care. All right, so we'll pretend it all came in right, but now it's organized this way. So if you go into Desmos and try to paste that in, you get something that doesn't look anywhere like what you want it to look like. All right, so what you do instead, yeah, I only copied the 13 for some reason. So paste the transpose, and now you have it in column form, and copy that into Desmos. And now you have it formatted the right way. All right, so, it's public service, I guess. Should be helpful. I mean, obviously double check to make sure that the picture insert copied the data correctly, but I didn't type a single number, and it's all in Desmos now. All right, so that's kind of what I'm after there, or at least that was the point of this presentation, if you will. All right, so